Start recording. Good morning. Today is Thursday, January 6th, 2022. Okay, and today we're going to start the last chapter of this course. Today's session, we will review or explain how to analyze simple structures composed by frames. Okay, it's like having beams and bars. Okay, that will be presented by Engineer Isaac. And before that, according to the recommendations that we have received from CICE, I'm going to make a couple of questions just to see that you indeed have seen this. If you have not done this, please be aware that this is the procedure that you have to follow. You have to review the material before class. But in any case, the whole process will be reviewed by Engineer Isaac, will be explained by Engineer Isaac. Okay, but it's better if you try to read the material, do the exercise before. Okay, so I'm going to do this quick review. And then Engineer Isaac will be reviewing the whole thing. And at the end, there is an example that we would like you to do in class. Hopefully, there will be some minutes at the end of this session. So if you have problems with that exercise, here it is Engineer Isaac, so he can explain how to solve those issues. If not, at least we have started, and after class, please try to practice. Okay, that's the agenda for today. So, can you see my screen? Can you see people on my screen? Okay, so this is the first part of this chapter. And the idea is that you follow these instructions in order to learn how to use ANSYS to analyze structures composed by frames, simple structures, okay? And this is a very common recommendation. If you have problems, try to write them down. So when we get together today, Engineer Isaac can solve those problems. Okay, here, this is the example that you will be working today. Okay, this is the same bridge that we employed as an example in the previous chapter. Okay, but now you see that we have included the loads because we have to continue not only preparing the geometric model. Now, in today's session, you have to analyze this structure. So you need, of course, the loads, and we have to emphasize that we are simply supported on both ends. So here, this is the process that you have to follow. People, did you have the time to complete this exercise? Anybody had the time to complete this exercise?
Yes, doctor.
Okay, so can I ask you, what is the equivalence of this step, preparing the mesh, in the material that we explain in class? What's the equivalence between this and how did we call this process in class?
Discretization.
Exactly.
Discretization.
Exactly. So you partition the domain and you are going to analyze each one of these elements one by one. And then you are going to form a very large matrix. We don't have to worry about that. It's internal. But this is what we're doing. Okay. And remember that this is associated with the convergence of the solution. Okay. As you decrease the size of these elements, you are supposed to get closer to the exact solution. Good. In the next step, okay, you have to insert, okay, the supports, okay? On the ends, on the two ends of this bridge, okay, we have simple support. Now, what do you think would happen if you do not include this step in your process? Anybody? What do you think would happen?
We can solve the problem.
Exactly. You cannot solve the problem because remember that the matrix, the stiffness matrix, is singular. So the determinant is 0 or it has not inverse. So the solution has no unique solution. I'm sorry, the system has no unique solution. Okay, so you need to include supports in order to see in the class, the way we mention is, or we describe it, is that there is no enough boundary conditions. Okay, when you forget about, or you, for example, do not include enough supports, what the program will tell you is that you have rigid body motions or something like that. Okay, so if you have an instructor, okay, you can deform it, and then after it is deformed, you can take it and move it some other places. So as you move it, okay, the solution is different because the values of the displacement are different. But since you do not change the deformation, the stresses which are inside the structure don't change, do not change. But you have many solutions. Okay, that's what that's the program is telling you. Okay, in our class we said we have no enough boundary conditions, or the program says that you have rigid body motions. So the solution is not unique. That's what they're telling you. Good. And the next step is, first you have to include supports, then you have to include loads. What would happen if you have no loads in your system? Of course, the system will not deform. So you have the structure, you have the supports, but you are not applying any force on it. So just the system is sitting there, so the stresses are 0. Okay, so of course you need to include not only supports, but also loads. Okay. And finally, in ANSYS, what you have to tell the program is what results you want to obtain, or you want not, yeah, you want to calculate. Okay. Remember, okay, that when you solve the system, okay, you have the displacement of the joints. That's the solution. Then you can take these joint displacements and go and calculate the internal forces. And also, with internal forces, you can calculate stresses. Okay, but the first step of the solution, that's what he does, is just to solve for the joint displacements. If you have something else, then you have to tell him, what do you want to see as a result? You want the displacement, you want the internal forces, you want the stresses. Now, when you say stresses, remember, there are many stresses. So all of that, you have to tell the program. What do you want him to tell you or to show you? Okay, so this is the last step. Okay, did anybody get the solution for this problem, structure problems? Did anybody was able to complete this exercise? People? Did anybody complete this exercise?
Yes, doctor. But I got it wrong because I put a fixed support, no simple support.
Okay, that's no big problem. And why do you think the value that you obtain is correct or not?
I didn't analyze yet. I just click and
No, but
click solution.
okay. Did anybody else?
Share?
No, right now, don't worry. Did anybody else complete this exercise?
I got a value, yeah. I got like
0.8 millimeters of deformation.
Okay, and do you think that's correct?
Considering of the size of the structure, might be correct.
Okay, how about the sign?
Yeah, the design, yeah. But I also put fixed supports.
Oh, that's fine, that's fine, that's fine. What about the sign of the displacement?
Yeah, the sign is correct.
How do you know?
Because it showed me the deformation.
Yeah, but
It
in
showed me
what direction? In what direction?
Downwards.
Yeah, that's the answer.
Yeah.
Okay, so remember, okay, you get the solution, but you have to ask yourself, does that make any sense? At least you have to check the sign of the deflections. Sometimes a 3D structure can play you full. But in general, that's something that at least we have to check the direction. Okay, Engineer Isaac sent you a file. He put it in the seed web, right, Engineer Isaac?
Yes, doctor. I posted
Okay.
the Aula Virtual.
So please, people, everybody, go to the Aula Virtual and download the full exercise that Engineer Isaac will be working on today. Did anybody was able to download it just to make sure that everything is fine? Somebody can confirm me that he or she was able to download this file? Anybody, please? Anybody? Okay, Mr. Nevares is saying that yes, so we're fine. Okay, good. So now let's go to Engineer Isaac. He will go on with this exercise in detail. Engineer Isaac,
Okay.
we'll listen to you. Go on.
Okay, and good morning, students. So we're going to see chapter 5 that is about structural analysis using a computer package. In the previous classes, we saw the pre-processing part, remember? So in this part, we saw the definition of the model, preparation of the geometrical plan, and generation of the surface and exporting. So in this part, we did two examples, right? The first example is the bridge using being element or bar element. The other exercise was applied with a statement, and this model we draw in the Rhino and then imported to the ANSYS, right? So in this part, we are going to continue today with the example of the bridge with the processing part. The processing part consists to define the structural property. It means the mechanical property of the material, okay? And then define the domain partition, that is mean the meshing, and then define the supports or load, and then select result parameters. For example, deflection, stresses, axial force, so on. And finally, it's very important, the post-processing part. You have to check convergence that is related to the mesh, and then checking result, if this result makes sense, and then you have to analyze, okay, is this structure fail or not, and so on. Okay. Okay, this is a an example that we draw in the previous class. This is a bridge. The unsupported span is 10 meters. The height is 5 meters. And then the profile of this beam is I beam. The cross section is I beam 8 inches per 4 inches. Okay. You notice that the total load is 20 tons. So imagine that a car or a bus is passing through the bridge. So when this bus is located in the middle of the bridge, the load is supported in these 3 joints. So this total load is located in these 3 joints. So you have to push this force. Okay. Also, you have to keep in mind that the certain when you apply this load, certain element will be in tension and other in compression. So you have to analyze after. Okay. Okay. So go on. In order to continue, you have to click on model and then assign the materials. By default, ANSYS use structural steel, but you can create a new material and assign, for example, aluminum or other material. Okay. Then in mesh, you can set up the element size. In this case, we will use 20 millimeters. Remember the units. In this case, the element size is 20 millimeters. When you create a mesh, if you don't notice the units, always the structure will be distortion. So you have to see, or you have to worry about the units. Okay. So this is the mesh. You have to click on general mesh. Then you have to specify the force as simple support. That is mean the boundary condition. So in structural insert, there are 2 parts. The first parts correspond to assign the force on the structure. You can use pressure, hydrostatic pressure, force, remote force, bearing loads, moment, line pressure, and so on. If you can specify the boundary condition, you can use this other part, the second part. So fixed support, displacement, remote displacement, frictional support, cylindrical support, simple support, fixed support, and elastic support. Okay. Then you can set up the force and simple support. So in this case, you have to set up 3 force in 3 joints, right? So for the first joint, for example, for the first joint, you can put the value of the force, select this point with this icon, and then specify the value using component defined by no vector. Instead of vector is component. Okay, in the y direction, because this is the reference system. So in the y component is minus 78,400 400, okay, newtons. So in this direction. The same for the other joints in the force 2 and force 3. So similar to assign the simple support in each border. So in the left point and the right point. So you have to insert simple support and then select this point, the left point, and also simple support to the right end. Okay, this is the result about boundary conditions and loads. Olivares, you have a question? Tell me.
Good morning. Yes, the internal joints between the same part of the structure, what does ANSYS consider it among them?
Okay, we draw this bridge using line, right? So you can put force using select lines or points, because we use element being element, right? Is your question is Nevares?
I meant, well, if the beam, like for example, in the top of the structure, would you consider ANSYS?
In the top.
Supported? It is simple supported. How we will understand it?
In the top.
Yes, just as an example, because we are just fixing simple supports in the instruments.
Okay. Okay. So let me come back. Go back. Okay, this. So you see that maybe you can you can use fixed support, but the what is this word? The word situations is simple support, right? So for that reason, I will use simple support, and in the top is the connection of this beam. I don't put any boundary condition, because I would analyze all the structure, no part of the structure. Nevares?
Yes,
If I analyze half of the structure, I will have I have to put a certain boundary condition in this part, in the middle.
Yes, what I'm asking is, what is ANSYS taking in that joint?
Simply
is ANSYS
supported, not displacing.
in the all other joints?
If you are not specifying any support, then ANSYS will assume that it is free to move in any direction.
Okay.
Like a friend.
Exactly. So
Okay.
if you know the support of one joint, then you have to specify. That's what Engineer Isaac was explaining you. If you assume that that support is clamped, okay, put it as clamped. But it is always a good idea, as Engineer Isaac said, to consider the other end, the other assumption would be that that end is simply supported. So you can take both and analyze the structure. But in the other joints, you see that there is no support, then you just leave them. So the loads and the stiffness of the structure will define in what direction they're going to move.
Thank you.
Okay. Yeah, I continue. So that we defining the boundary condition, and then so the next step is to set up the parameter of the solution that you want to see. For example, if you want to see the formation in the x-axis, you have to insert, you have to go to this in this path, insert the formation, and then select the directional deformation. So you can change the orientations in the x-axis, on the y-axis. So you have to create these parts and then repeat this step in the y directions. Also, if you want to see axial force, you have to set up, you have to put beam results and then select axial force. So you see that there are many options in the beam results. For example, bending moment, torsional moment, shear force, because this is element, beam element, okay? Also, you can obtain the reactions in any support, in any support. In this case, we use simple support. So you have to follow this path, prove, select for reactions, and then you have to specify the reaction in any support. In this case, the simple support that this simple support is in the right, in the left end. Finally, you have to click on solve, and this is the final setup that you want to have. Okay, this is boundary condition and loads, and then the parameter of the solution that you want. So this is processing part. So now you have to analyze the result. For example, this is the deformation in the y directions. So these deformations is in the global reference system. No, it's not local, it's global reference system. So you see that in this point, in the middle, in the y-axis, practically is equal to 0. So this value is compared to the between the results obtained by the Python program. So you see that in this point, the displacement in the x-axis is equal to 0. So that makes sense. The same for the y-axis, the y deformations. So is -2 millimeters, and then you see -2.5 millimeters. So when you apply force in the y-axis, these points move downward. So that makes sense. Okay, for the deformation. If you see reaction force, for example, in the left ends, you see the force reactions in the in the component in the x-axis and the component in the y-axis, and compare with the Python programs, as you see that the values in this component practically is the same. Okay, so you see there compared to this. Okay, but it's the same. So also you compare, this is reaction 4. Also you compare the axial force. For example, if you want to analyze part of or half of this structure, so you see that in this part, these elements, the axial force is in compressions, and the other part also in compression, and the vertical elements, so is in tension. Okay, if this value was compared to the Python program, and you see that the axial force for each element is close. Okay, the same for the others, and the same for the vertical element. So you see that this value is close to the value obtained by the ANSYS. Okay, so if you want to analyze when you apply force, so you have to check that this element that is in compressions maybe buckled or not. So this is analysis. Okay, and that's all. Wakon, you have a question, right? Wakon? No?
Yes,
Okay. Okay.
we can see the table in the program.
Okay.
Well, pardon.
So this is the table, the program, the axial force. What table do you want to see?
Where we can see the table in the program.
I don't understand.
The table that you see here are the results that,
Okay.
that we obtain using another application. Okay, that's what you did in your project. You analyze this structure with the Python program, okay, and these are the results that you obtain. So what engineering is explaining you is that you get these results using ANSYS and these results using the theory that we presented in class. And these results are very close to the one that we obtained with ANSYS. That's what they're telling you. So this table here, you obtain it with your own program. And this is what ANSYS will give you. These values, all these values here, you will see them in the screen that ANSYS presents to you. Wakon?
Yes, Dr. Chess.
Okay. We're going to do in the ANSYS program, maybe in this part, we have the first break.
Yeah. Okay, so we're going to have a break here. And when we return, please, everybody, make sure that you have opened the ANSYS program so we can start applying this example by yourselves. Okay, so you can practice this. Okay, so let's take a 5-minute break here.